Today we're going to learn about the derivative and the tangent line problem. Already we've seen this whole idea where a tangent line is created, like the blue line you see here, and we have to find the slope of it. We call that the derivative. What we're going to do to try to get around this is to create a secant line. A secant line goes through 2 points. The first point is going to be the original point of tangency. I'm going to call it x comma f of x. That way we're not going to restrict to a particular function. This will be a generic equation. I want to move over just a little bit, actually specifically the value of h to the right of that, and create a new point that's h units away from the original point. So here again, this is really generic and not a specific numerical value. If that's the case, the x-coordinate is x plus h, and its corresponding y-coordinate would be f of x plus h. The idea is we want to try to put those 2 points as close together as possible, but we saw already on the applet that you did that you can't actually put them on top of each other. If that's the case, h is going to be 0, and the slope is going to be undefined. So what we'll do is actually find the slope between these 2 points, keeping them apart and h distance apart. I started with these 2 points. Then using the slope formula from algebra, I filled in the information from each of those points. The only reduction that really happens is in the denominator, the x's actually cancel and I get that h. And here again you see the problem. H cannot equal 0. But that's really what I want. I want those points to be split apart, or not to be split apart, to actually be on top of each other. So this is where we're actually going to make use of the concept of the limit. We call this part the difference quotient. I'm going to take that value and put x, or h, as close to 0 as possible. So now the difference quotient becomes a derivative. So f prime of x equals the limit as h approaches 0 of f of x plus h minus f of x all over h. H really isn't 0, it's just getting as close as possible. This is the mathematical definition of the derivative. So in order to find the slope of the tangent line, I'm going to have to apply this formula to each and every function that we have. Let's look at the first example. I want to find f prime of x if the function is f of x equals 2x minus 3. So first, I'm going to set up the definition. This should be your first step every single time. Next, I'll fill in those values. Here, f of x plus h refers to the function. Everywhere you see an x value, I'm going to replace it with an x plus h. So it'll look like this. 2 times x plus h in parentheses minus 3. The next thing that gets substituted in is the original function. I'm going to subtract off the original f of x. In this case, 2x minus 3. This is all over top of h. There's a lot of algebra that needs to be done next. Direct substitution still doesn't work, so I have to keep going. So 2x plus 2h minus 3 minus 2x plus 3. Note how I went ahead and I distributed the negative sign to both parts there. This is still all over h. There's a lot of cancellation that occurs. The minus 3's go away. The 2x's go away. And now the h is reduced. In this case, direct substitution doesn't really even make sense anymore. There's no h left in the problem to substitute 0 into, so the limit itself is just 2. That tells me that the derivative is 2. Now that I think about it, that kind of makes sense. Look at the original function that I gave you. This original function is a line, and on a line, all the tangent lines have the same slope, the same constant slope. From y equals mx plus b format, we know that the slope was supposed to be 2. And we found 2. It means every single tangent line has a slope of 2. The next one will be a little bit more interesting because this isn't a line anymore. This is the function x squared plus 1, and I want to find its derivative. So I'll start the same way. This is where it gets a little bit more difficult. When you substitute x plus h in for x, it becomes x plus h squared plus 1. Then I'll subtract off the original function and put that all over top of h. This is going to create a lot of extra work. What that's telling you to do is take x plus h and square it, or in other words, write it twice and then FOIL it. When you FOIL x plus h quantity squared, you get x squared plus 2xh plus h squared. Then we have a plus 1 attached at the end, a minus x squared, and a minus 1. Here again, I'm distributing the negative to both parts there. As before, direct substitution still fails, and there's some cancellation that should occur. The 1's and the x squareds. But now direct substitution is still failing. There's an h in the denominator, but I can't stop there. I have to make use of some of the things that we talked about in the first chapter. I'm going to try to factor this. There's an h in common to both parts of the numerator that I'll take out. Now I can actually cancel. Direct substitution at this point is actually going to work. When you see the h, you fill in the 0. And I get 2x as an answer. That means the derivative is equal to 2x. This is kind of different. I mean, that's telling you that the slope of the tangent line is 2x. Why do you think there's a variable in the answer? Picture the function x squared plus 1 and all the different tangent lines that you may see on it. Some of them are positive, some of them are negative, maybe even flat in a 0 slope. This derivative is actually going to be a generic formula for any point that you want to work with on the curve. So just to look, let's say I wanted to find the derivative at -1. In order to do that, I'm going to substitute -1 into the derivative formula. And if you remember, the derivative formula was 2x. So the slope of the tangent line at -1 must be -2. I could do that for a lot of other points, like 0 for instance. If I wanted to find the slope of the tangent line at 0, I would substitute 0 in for x and get 0 as a slope. I could do it at x equals 1. F prime of 1 equals 2. All of these are different values and represent the exact slope of the tangent line at those specific places. The last example, we're actually going to go from this one and write an equation of the tangent line. I have the slope. I have an x value. That's enough to write an equation. Only thing I'm really missing at this point is the y-coordinate. But if you have the original function, there's a way to find it. So I have x equals -1. The corresponding y-coordinate can be found by substituting into the original. That would be -1 squared plus 1, or 2, and I have the slope. Remember, the calculus is what gives you the slope of the tangent line. So y equals mx plus b finishes this up. B is 0 for this particular one, and the answer is y equals negative 2x plus 0. It's the slope of the tangent line. Your assignment is to complete page 104, numbers 14, 8, 17, and 29. These are all examples in varying levels of difficulty of finding the derivative using the mathematical definition. Some of them may ask you to find an equation of a tangent line, but you don't need to go that far today. We'll do that much later. So for today only, we're going to go ahead and use the mathematical definition to find the derivative, the generic derivative. Some of the problems do ask you to substitute a point in and to find a specific numerical value. That would be good practice, so go ahead and do that. The answers will only be in the back of the book for a couple of problems, so I left the solution manual available to you so you can check your work as you go through. One thing to watch is that foiling process whenever you have an x plus h. It's going to be really important you do neat and organized algebra work. In addition, all of the work you do needs to be neat and organized. Otherwise, the algebra is going to get messed up and you'll end up with the incorrect answer. So practice with these 4 problems. Like I said, they go from easy to difficult, and they'll give you a good idea of how to use this mathematical definition. And I think you'll find while you're working on the assignment, there's got to be a better way. This is a lot of work, and these problems are pretty small functions. So tomorrow, what we'll do in class is actually look at how we can completely avoid everything that we've just talked about. Go from and start to make some shortcuts to avoid everything we've done, and go from finding these derivatives with a mathematical definition to using shortcuts that people have found and created just to get around it. So that'll be tomorrow.